All right, we are tasked to give a combinatorial proof of this identity here. A combinatorial proof is going to be a counting proof. So we're going to have to do some counting and describe different ways to count something. Here we have the left-hand side. I'm just going to abbreviate it like that, and the right-hand side. So for any combinatorial proof, we're going to use the same approach. More or less, here, that means we're going to come up with some S that we can count in two ways, that we can count using the left-hand side and the right-hand side. So we're going to find S that can be counted in two ways. And then next, we're going to prove that S can be counted using the left-hand side. Finally, prove that S can be counted using the right-hand side. And the intuition here is that if the size of S equals this, and it equals this, then this has to equal this, right? By that kind of transitivity of equality. Okay, great. Now let's actually implement this. So we have this lovely hint. Think about different ways to select a team with one member designated as its captain. All right, I'm gonna think about that. I'm gonna use that in my creation of S. And in both of the left-hand side and the right-hand side, I see that there are these two terms. So there's a term that's multiplied and a binomial coefficient. And that kind of lines up here with these two decisions we have to make. So ways, maybe I'll switch colors. So that's ways to select a team and ways to choose a captain. So I'm gonna make my S be equal to kind of the ways that we can choose a team and designate a captain, but using these numbers that we see up here, or these variables. So I see N choose K here. That kind of gives me the hint that maybe we have N people trying out for the team, and we have teams of size K. So let's say S is the number of teams where N people try out, and K people kind of are on the team. So maybe K people make the team. And each team has one captain. All right, now let's use the left-hand side to count the size of S. So this is our kind of step one. Here's our step two. So we want to prove that the size of S is equal to that left-hand side. So K times N choose K. Just really quickly, in case we forget, N choose K is our binomial coefficient, our good friend. The binomial coefficient N choose K is saying if I give you a set of size N, how many ways can you give me back K of those things? So K elements. So here, if I give you N people that tried out, how many different teams of K can you give me back, right? So maybe first we're gonna do that. So let's say first, of the N people who tried out, choose K of them to be on the team. All right, and that's gonna give us N choose K choices, right? Just kind of by definition. And then next, once we have our team, choose one of the teammates, and there are K of them, to be captain. Now, we could be really detailed and say that that means that there are K choose one choices, but we know that that's really just equal to K choices, right? And here we have described this decision process. So we have two decisions, and no matter what we make, what choice we make, which person we decide to let on the team, we know that in the first step there's N choose K choices, and in the second step there's K choices. So that hints to me that we can use the multiplication rule. And that means that we just multiplied these two things together. So that tells us that, maybe this is our big therefore. Therefore, the size of K is going to be equal to K times N choose K, which is equal to our left-hand side, right? All right. Next, we're going to do the step 3. So we want to prove that the size of S is also equal to the right-hand side. So that's n times n choose 1, n minus 1 choose k minus 1. All right. So in general, maybe if you have these two terms, a good strategy to try out is to change the order of our decision process. So let's see what happens if we do that here. So maybe instead of first picking who's going to be on the team and then choosing the captain, we first pick the captain and then choose the rest of the team. So let's say first of the n people who tried out, pick one to be captain. What a powerful person. They are being put on the team and being made captain all in one fell swoop. Okay, so that's n choose 1 equals n possible choices for captain. And next thing we're going to do, maybe we even give this captain full authority to pick who else is going to be their teammates. But next what we're going to do is fill the rest of the team. So there are k minus 1 spots left on the team, right? Because the captain's on the team. And there are n minus 1 people left, right? Because the captain's already been chosen, so we have to choose new people. So that gives us n minus 1 choose k minus 1. By the same logic we used before, we can use that multiplication rule here. So we're going to multiply these two terms we just got, and that's going to give us n times n minus 1 choose k minus 1. So that's going to be equal to the size of S, right? We just explained exactly how we counted it. That's going to be equal to the right-hand side. And then our secret fourth step here is going to be our conclusion, right? Very important to summarize your thoughts. So therefore, the size of S is equal to the left-hand side, which is k times n choose k. And the size of S is equal to the right-hand side, which is n times n minus 1 choose k minus 1. Therefore, kind of by the transitivity of equality, we have that this identity holds. So k times n choose k is equal to n times n minus 1 choose k minus 1. And then whatever QED symbol you want. Okay, thank you very much. Bye-bye.